Okay, so we're going to start lecturing here on chapter 2, which is measurements. We are covering chapter 1 as well very shortly. I'll probably post up a very short pre-recorded lecture out of chapter 1. There's not much going on in chapter 1 really, other than maybe like the scientific method is kind of the only thing that you maybe have to worry about. So like I said, I'll post up a little very short lecture on it. Other than that, there's really not too much at all really to worry about probably from chapter 1. So we're going to kind of get right into it here then and kind of start talking about chapter 2. And chapter 2 is all about measurements. We're going to talk about obviously units. We're going to talk about how to take a proper measurement. We'll talk about some temperature conversions. We'll talk about a really important thing as well in this chapter, which is dimensional analysis. And dimensional analysis is really, as we will see and sort of talk about, how you show kind of your work in chemistry, and it's how you're expected to show your work. And as we will see, it's basically just using conversion factors to do calculations where you show the units and things of that nature. And that's a really, although it's in the early chapter here, is actually a really important sort of skill to pick up and get used to showing your work that way. Again, as you continue on in chemistry, they will expect you to kind of show, when they say show work, that's basically what they're going to want you to ultimately sort of show. We will finish up the chapter here, I think, talking about some density at the very end. So let's get into it. So one of the really important things when we talk about measurements is units. And the idea of units is really important when you take a measurement. For example, if I wrote, 150, we really don't know perhaps what that means, right? So I say, hey, what does that mean? That's 150. Could be $150, right? Which would be great. It could be 150 pennies, still great. Not as great as the first one. Maybe if it's 150 apples, good if you're making some apple pie or something like that. But the number by itself really is useless as there's no units, no frame of reference for what it represents. So when we're in chemistry and we're taking measurements, a number by itself is no good. We need a number and some type of units. Maybe they are grams. So one thing you want to always sort of think about when you are taking a measurement, when you're recording a measurement, especially when you're in lab, which is very common where people sort of forget to do these things. You always should have a number and a unit. And again, the unit really does give you a reference to what that value means and what that number means. The place where people really break down in terms of not using units, where they definitely should use units, is really in calculations. And as I just mentioned a second ago, we're going to talk about dimensional analysis in this chapter. And that is a process where it's all based on units and units canceling each other out. So you also want to make sure you're in a habit of, when you're doing calculations and when you're showing work, that you also show units in the calculation part, not just like the final answer or anything like that. Again, it should be throughout the whole thing. So units is really the part of the measurement that gives us that reference point of what the value means. There's kind of two widely used system of units. There's the English system, or sometimes referred to as the US system, which we use here in the United States. And then pretty much everybody else uses the metric system around the world. And as you can imagine, when everybody sort of got smaller and people are sort of interacting with each other in different countries, that could create a problem if, we're doing inches here and maybe somebody's doing centimeters somewhere else. So around 1960, they had a conference on weights and measures. Sounds like a lot of fun. And they came up with sort of a standardized system of units, which is known as the SI system. And you'll sometimes see that a lot in chemistry. The SI unit for mass is this, or the SI unit for uh, temperature is this. SI is the International System of Units. And for all purposes, it's pretty much based on the metric system, kind of one out there. So it's really sort of based on the metric system. Um, but it is sort of that standard unit that people sort of use. And here are those standard sort of SI units for different types of quantities. Mass, it's the kilogram. Length is the meter. Time is seconds. And one that you may not be too familiar with yet, but you definitely will be familiar with after we are done here in chemistry, and that's temperature. And Kelvin is the standard unit of temperature. That's also something really important to keep in mind because, frankly, as you will see as we go through these different chapters, pretty much if you're doing anything with temperature, Kelvin is pretty much where it needs to end up in terms of units. It's always kind of the first thing, or one of the things that you always do is kind of convert the temperature into Kelvin. There's only one calculation we'll come across in chemistry here, and probably your entire chemistry career, where you'll actually leave it outside of Kelvin, but almost 99.9% of the time, you always want that temperature sort of in Kelvin. The other really important thing that's important to know is what the unit represents. So if you're talking about a kilogram or a gram, you are talking about mass, and you're not talking about like a volume. If you're talking about volume, you may be talking about cubic centimeters, milliliters, liters. So it's really important to have that sort of understanding of when you see a unit, what type of sort of quantity or measurement it is referring to. So when you're asked, what was the mass of it, you don't say like 52 liters because that's like volume. So you want to make sure you do understand not only sort of what the units are, but what they do represent, what type of measurement that you come across. Now, let's talk about some of those measurements. The first one here is length, and the SI unit there for length is a meter. 1 meter is 39.37 inches. Um, that's a good little conversion there to know, yeah. And some very common units of length are centimeters, kilometers, decimeters, and meters themselves. 1 centimeter is 0.01 meters, or that is 1 times 10 to the minus 2 meters. These two numbers are the same number. One is written in scientific notation, which we'll talk about a little bit later on here in this chapter, and one is in sort of decimal form. That is definitely a conversion that you should know. And there is sort of the opposite, larger conversion of that, where there is 100 centimeters is equal to 1 meter. So that also is the same conversion. And I would definitely sort of know that because converting from meters to centimeters does occur a lot. 1 decimeter is 0.1 meters. 1 kilometer is 1,000 meters. That also is a very common sort of conversion to know, and does come up a lot. By the way, if you're not sure how we go from top one to the bottom one, we divide by 0.01. And that gets us up to that one there. And they are the same version as you go through there. So I would say very commonly in this class, and a lot of the chemistry classes that you come across, the millimeters are also on a unit that you see. There are, by the way, 1,000, another sort of conversion in terms of length, 1,000 millimeters in a meter. And that's another sort of conversion as well. All right. Now, as we saw there, very common with measurements is the metric system. We oftentimes will use prefixes to sort of change the meaning of some of those numbers. So these are some common prefixes: mega, kilo, deci, centi, milli, micro, and nano. I will say probably in your chemistry career, you will come across pretty much. So this is probably something that you need to know along the way here. I would say for us, very common ones that we will see: mega, kilo, centi, milli, and a little bit of nano. As you go through the rest of the classes, you really will pick up the rest of the ones that are in there as well. Definitely micro is a very common one as well. Now, there's a couple of different ways that you could use these sort of prefixes, and there's two sort of meanings, as you can see there. One is sort of a whole number, decimal sort of meaning, and one is really something that's in scientific notation over here on this side. And we'll see this as we continue on, but just to give you an idea of how to properly use this, which is something that people always, when they go to use this as sort of a conversion factor, they always tend to do it sort of backwards and in the wrong way. So when we look at something, say like kilo here, and you see kilo and it says it equals 10 to the 3, which a lot of times is very commonly how you'll kind of see it written. By the way, as I mentioned a second ago, that is really written in scientific notation. And really what that is 1 times 10 to the 3. And like I said, we will talk about scientific notation coming up here shortly. But what that means is when you see that number of 10 to the 3, it represents how much there is in the prefix unit I'm sorry, in one of the prefix units, that's how much there is in the base unit. So when we talk about sort of prefix unit and base unit, what I mean is if I had, for example, a kilogram and a gram, right? So they are both related to each other by the base unit here of grams, right? They both have grams in them, basically, right? Kilograms and grams. So if I wanted to use this as sort of an equality or a conversion factor, the proper way to use it is this would be like our prefix unit, and this would be really just our base unit. So in one of the prefix units, there would be 10 to the 3 grams, and that is the proper way to sort of use that. It is a very common mistake that people will go, hey, there's 10 to the 3 kilograms in 1 gram. And again, that's the backwards way and not the right way to do it. And it doesn't really matter, by the way, the what the base unit is. So if I were doing something else like kilometers and meters, in this case, our base unit is meters, it would work the same way. In one of the prefix unit, there would be 10 to the 3 meters there. And again, that is the proper way to use that. If you looked at something like centi, which is right there, which is, bless you, 10 to the minus 2. That, by the way, is 1 times 10 to the minus 2 in scientific notation. It would work the same way if I had a centimeter and a meter. In one of the prefix units, there would be 10 to the minus 2 meters associated with it. So again, that is something that very commonly people like to kind of do wrong in that sense and kind of use it incorrectly. You obviously, again, can use the same sort of number or the larger number, if you like, to give you the same sort of conversion. Again, though, if you go with the larger number, you also want to make sure you do it right. So again, there would be 1,000 grams in 1 kilogram in that case. Yeah. So you do want to make sure again that you sort of use it in the correct fashion. Any questions on that there? Okay. And we'll see this a little bit later when we start talking really about conversions and stuff like that. But again, these are sort of the prefixes that are used to change some of the meanings there. Now, this is a ruler, and again, it illustrates a common ruler and the difference between the English version and the metric version, as you are probably aware of. Up on top here, these are inches. On the bottom are centimeters. and 1 inch is exactly 2.54 centimeters. That is definitely a conversion that you should know. So 1 inch is equal to 2.54 centimeters. Top is inches, bottom is centimeters. Little guys down here are what? Those are? Those are millimeters, yeah? So the little guys there are millimeters. There are 10 millimeters in 1 centimeter, yeah? So 10 little dashes between each of the bigger ones, yeah? So inches on top, usually on a standard ruler, centimeters on the bottom, little guys on the bottom with the centimeters are millimeters. So volume is the amount of three-dimensional space that is occupied by a substance. Volume is length cubed, and the SI unit is actually meters cubed. And 1 decimeter cubed is a liter. 1 cubic centimeter is equal to 1 milliliter, and 1 liter is 1,000 milliliters. I would say definitely you should know these guys. And I would say probably in chemistry, these are the two that you kind of come across the most. Definitely the bottom one is one that we use a lot. And it's kind of for this reason, as you will see in the laboratory and stuff like that, when we take a volume measurement, oftentimes we do take the measurement in milliliters. But a lot of times when you go use that to put it into a formula, you need to actually convert it to liters. So that conversion between liters to milliliters or milliliters to liters is a conversion that we use a lot. So that 1,000 milliliters to liters is something that you'll use a lot throughout chemistry. The relationship of a cubic centimeter is 1 cubic centimeter is equal to 1 milliliter. They're basically the same. Sometimes if you're dealing with more like medicine, for example, a cubic centimeter is sometimes referred to as a cc. If you ever watch a medical show, right? Give the guy 5 cc's before he dies or anything like that. That's basically 5 milliliters. And cc is used as a cubic centimeter as well. Now, you maybe think to yourself, isn't a centimeter a length measurement? And you would be right. And there's a couple different ways that we typically get the volume of something. Clearly, we could take something in a piece of glassware and basically just read the volume of what's in there. Another way that we can sort of commonly get a volume of an object, especially like a solid object, for example, and that's something you'll do next week in lab, is actually we could take some measurements and we could take some length measurements. And if we measure something like the length times the width times the height of a a solid object. And if we take these measurements each in centimeters, we would get a centimeter times a centimeter times a centimeter. That will give us a cubic centimeter, which will equal the volume. So if you take a length measurement typically and you cube it for something that's like solid, you will end up with an actual volume. So each of these individual measurements here, these are all length measurements. But when you multiply them together, you will get a volume measurement that is there as well. And that is how we get to sort of our cubic centimeters, which again is a volume measurement. So if you see any sort of length measurement that has been cubed, it is really most likely going to be a volume that you're dealing with rather than a length sort of measurement. Any questions on that there? Now, mass is the amount, quantity of matter that is present in an object. Matter is basically anything that occupies space and has mass. So pretty much everything that you could touch or maybe not see. The fundamental unit of mass is a kilogram. And this is a table from your book of some common metric units for mass. Again, I will say for us, common units that we come across, grams, kilograms, milligrams are very common sort of units of mass. So kind of the same relationship that we talked about earlier. There is 1,000 grams in 1 kilogram. That again is something you should know. It's definitely used a lot. You could also use the kilo conversion, which is 10 to the 3, which is 1,000. There is 1,000 milligrams in a gram. That's also another one uh, that is used a lot. So one of the ways that we do get the mass of an object is to use a guy like this that we talked about when we were checking into lab. That is what is referred to as a balance. And we use it to weigh things and get the mass of an object. Now, as we talk about mass, there's an important sort of difference between sort of two words. They're sometimes interchanged or sort of used sort of together to sort of mean the same thing. And there is really a difference between mass and weight. And when we talk about mass, mass is sort of independent of the force of gravity, while weight is dependent on the force of gravity. So when we weigh something in the laboratory using a balance, we do refer to it as the mass. The mass of the object would be the same here, for example, and like on the moon, but the weight of the object, like the apple there, would weigh different here versus the moon because the moon has a different force of gravity than it does here on Earth. So when we do weigh something, which is the process that we do when we use a balance, we do refer to it as the mass of the object. So you should refer to it as the mass of the object. Balances actually are able to take subtract sort of the force of gravity and take it out when we weigh it on there. So we are getting the mass of it rather than the weight. So when you're talking about something that you weigh, you should refer to it as the mass and not the weight of the object. Now, let's talk a little about temperature conversions. And there's really sort of three temperature scales that we will see here. And the three temperature scales is degrees Fahrenheit, degrees Celsius, and the big one for chemistry, which is Kelvin. Now, the main difference is obviously the conversion between them, but one of the main differences in terms of how you write the unit is, as you can see, it is degree Fahrenheit with the little degree symbol here. It is degrees Celsius. Here for Kelvin, we do not use the degrees symbol, so it's just Kelvin. So if you had 273 Kelvin, that is how you would say it. You wouldn't say 273 degrees Kelvin or anything like that. It would just be Kelvin. The other ones we do. Truth be told, outside of this chapter, you're probably not going to see a lot of Fahrenheit and things, I would say, in chemistry. In chemistry and in science, we typically deal with Celsius, and as I mentioned, kind of converting to Kelvin is really the two common ones that we see. Fahrenheit is the scale that we commonly use here to talk about the temperature outside or the temperature of our body. On the Fahrenheit scale, water boils at 212 degrees Fahrenheit and it freezes at 32 degrees Fahrenheit. Celsius is more of a metric system unit for temperature. Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. That is definitely something that you come across a lot that you should know. Those two sort of temperature values for water is really something that does pop up a lot as we go through it. A third temperature scale used to be called the absolute temperature scale. It was later renamed for a guy named Kelvin, and they now call it the Kelvin scale. And water boils at 373 Kelvin, and it freezes at 273 Kelvin along the way. As I mentioned a second ago, pretty much outside of this chapter, not going to see that Fahrenheit all that much. We definitely do see Celsius a lot. Kind of like what we were talking about earlier. Very common when we take temperature readings in the laboratory. Our thermometers are in Celsius, and we take the reading in Celsius. Very, very common. There's pretty much not very many formulas in chemistry that you use Celsius in the formula. You got to use Kelvin. So the conversion between Celsius to Kelvin is one that you just kind of just automatically do most of the time when you're doing a calculation. Occasionally, you may need to convert back from Kelvin back to Celsius. So that conversion, kind of the Celsius to Kelvin, is probably the one you'll do the most. And converting from Kelvin back to Celsius is one that you'll do probably the second most. Like I said, very, very uncommon to see sort of Fahrenheit a lot of the times. Here is temperatures of those three units, and it's really the difference between where water kind of freezes and boils on these scales, which gives us our conversion factors that we use. On the Fahrenheit scale, you're looking at about 180-degree difference. On both the Kelvin and the Celsius scale, the difference between freezing and boiling is about 100. And that, like I said, is really the basis of how we convert between the different units. And let's talk about those formulas here to convert. And my bad here. We're going to, because they want you to use a very specific number here. So first off, the temperature in Kelvin is going to equal the temperature in Celsius plus 273.15. So they do want you to use here that number with the 0.15. I'll be honest with you, most places and most people kind of dropped the 0.15, but here they have very special rules, so they like to keep the 0.15 here. So we will keep the 0.15 on those numbers. A lot of places, like I said, will just do 273 without the little 0.15 part of it. So if you need to do the opposite, which is go from Kelvin back to Celsius, the temperature in Celsius will be the temperature in Kelvin minus 273.15. So definitely need to know, yeah. Now, when we go between Fahrenheit and Celsius, we have a couple different sort of equations for that. The first one is if we want Fahrenheit temperature, we take 1.8 times the temperature in Celsius plus a 32. If you have Fahrenheit and want Celsius, the temperature in Celsius would be temperature in Fahrenheit minus 32 divided by 1.8. So these guys as well, make sure you know as well. Again, they will not be provided for you along the way. Now that 1.8 number is really the same number that you might have learned as a fraction. 9 over 5 is sometimes how people do this conversion. So you can use 9 over 5, which is 1.8 along the way. Now, if you have the temperature in Fahrenheit and you need Kelvin, you got to go from Fahrenheit to Celsius, Celsius to Kelvin, and vice versa. If you have Kelvin, got to go all the way down to Fahrenheit. You got to go Kelvin to Celsius, Celsius to Fahrenheit along the way. Again, the top box there with the Kelvin and Celsius, probably almost 100% of the time you're going to use one of those in terms of the temperature, and probably most of the time it is going to be that adding the 273.15. Now, let's talk a little bit about significant figures, but not really officially here, and sort of what we do when we want to give the proper answer. And the only thing that we're doing is just converting temperature. So if we're just taking a temperature value from one unit of temperature to another, like maybe I'm converting Celsius to Kelvin or Fahrenheit to Celsius, we do not, typically speaking, follow strict significant figure rules in terms of our answer and what we want our answer to be. We follow a more general rule, and the reason for that is there's a lot of variation in terms of like that 1.8 number. Some people may use the fraction, some people may use 1.80, some people may use 1.8, and there's a lot of variation with it. So the general rule is if you are simply just doing a temperature to temperature conversion where you would use one of these sort of formulas, your answer should look like the original number was. So if the original temperature value was a whole number, when you do the conversion, you should end up with a whole number. If the original temperature value went to the first decimal place, after you do the conversion, your conversion should go to the first decimal place. So that is not really strict significant figure rules. That is the general rule that people use when they are simply just doing a temperature to temperature conversion, and that's the rule you should follow. So basically, straight up temperature conversion, whatever that original number was, however far it went in terms of decimal places, no decimal places, when you convert the value, you should keep it the same. So why don't we try some here? Grab a calculator there, take a few moments, and for each of these, do the conversion and see what you end up with. We got 28.5 degrees Celsius. What is it in Kelvin? 41 degrees Celsius. What's it in Fahrenheit? And 160 degrees Fahrenheit. What is it in Celsius? So grab a calculator and make sure it works. Okay, let's take a look and see how you're doing. The first one here, temperature is 28.5 degrees Celsius. We're looking for Kelvin, so we want to use our formula that we saw there. Again, the temperature in Kelvin will equal our temperature in Celsius plus 273. Again, they do want you to use the 0.15 here. So popping those numbers in, we're going to go 28.5 plus a 273.15. And on your calculator there, you're going to end up with a 301.65, and this would be Kelvin, if I get my K right in there. Now, again, as I was talking about a second ago, in terms of how we want to give our answer, because we're simply doing our conversion of temperature to temperature, when we look at the original number here, it does go to one decimal place, which means we actually do want to end our answer here at the first decimal place. As you probably know, we follow basic rounding rules, which means if I look to the right there, that is a 5, which means I am going to round up because it's 5 or more. And that would give me a final answer of 301.7 Kelvin here. Any questions on that one there? Now, again, there is no degree symbol that's written for Kelvin. Again, it's just a capital K. Any questions on that one? Taking a look at the next one, we have Celsius, and we're going to Fahrenheit. So our temperature in Fahrenheit equals our 1.8, our temperature in Celsius plus a 32. So putting in our numbers here, we got 1.8 times 41 plus a 32. So again, if we put that into our calculator, 1.8 times 41 hit equals plus a 32. Going to go 105.8 is going to be staring at us here. And this would be degrees Fahrenheit. Once again, in terms of how we want to give our answer, we want to look at the original number here. And in this particular case, the original number is a whole number. So we do actually want to round this to the nearest whole number, which would put us here. Once again, looking at the number to the right, it is above 5, so we would round up, and that would get us 106 degrees Fahrenheit. Yeah. Any questions on that there? Lastly, here we have degrees Fahrenheit, and we're going to Celsius. So our formula there is temperature in Celsius, Fahrenheit minus 32 divided by 1.8. So popping our numbers in there, our Celsius is going to be 160 minus 32 divided by 1.8. So we go 160 minus 32 divided by 1.8. I might want to hit the right number there. Try that again. 1.5 is kind of close. We're going to end up with 71.1, a bunch of ones on there, degrees Celsius. Once again, when we look at our original number here of temperature, it was a whole number. So we would want to go to a whole number here. So that's going to bring us to that guy right there. It's going to be a 71 degrees Celsius. Any questions on that there? Couple calculator reminders, especially maybe on the last one. You probably don't want to punch all that in as one whole thing. My recommendation would do 160 minus 32 hit equals, and then divided by 1.8 and not try to punch it all in at once. You may end up with the wrong answer if you do that. Yeah. Any questions on any of those? So once again, as I mentioned, this is the general rule that we follow strictly for just a temperature to temperature conversion. Original number, however far it went to, is what your converted number should go to. All right. Again, you do need to know how to do all those conversions from Fahrenheit, Celsius, Celsius, Fahrenheit, Celsius to Kelvin, and Kelvin to Celsius. As I mentioned earlier, as we move out of this chapter, pretty much it's going to be strictly kind of that Celsius to Kelvin and Kelvin to Celsius conversion you're going to see pretty much the most. Now, as we talked about earlier, right, it's important to understand what the units represent. So when I say 523 Kelvin, I am talking about a temperature. Yep. And when I say 25.36 liters, I'm talking about a volume. Yep. And 15 meters is a length. And 63.3 kilograms is a mass. Yeah. So again, understanding what those units represent is really, really sort of important. All right. Now, when we take measurements or sort of observations, we sometimes deal with two types of sort of observations or measurements. Really, one's a measurement, one's more of an observation. There is qualitative, and qualitative consists of just really general observations about a system. So if you're making some type of qualitative observation, you're really not doing a measurement. You're just really observing what is happening. Like, hey, it turned purple, it was pink, there was rainbow and unicorns coming off. There's a solid that made, and things like that. Really, qualitative has nothing to do with an actual measurement. In fact, if you continue to do on with chemistry and you do get to chemistry 1B, you will do a bunch of terrible experiments known as qualitative analysis. And these are all experiments where you do a bunch of lab work where you do not measure things out. You go like, yeah, like 20 drops is like a milliliter. That's close enough. If I miss it by 1 or 2, is not that important. There's really no calculations, for example, involved in that type of experiments. It's all about you put these things together, you get like a yellow solid form, or you get a red solid, or you get like a blue lake of something's form. And it's all really more observation and general things that are happening. Now, different to that is quantitative. And when we do something that's quantitative, that comprises of numbers and values. And that really is measurement. So when you qualitatively fill up 5 milliliters of water, you may just start counting drops and go, it looks pretty close, right? When you quantitatively fill up 5 milliliters of water, you want to be right on the nose in terms of how much water you have in there. You want to be exactly at that. So quantitative are measurements. They involve numbers, they involve units, and in most of your chemistry career, when you're in the laboratory, quantitatively is really what we want to do. We want to really be pretty exact in what we're measuring out and what we're looking at. Again, if you get to 1B, you'll do a bunch of experiments where you don't have to be super careful about measuring everything out. It's more qualitative. It's more of those sort of observational types of things. When we're in the lab, in general, we do want to actually do both of those things typically when we are doing experiments. So when we do an experiment, for example, we don't just want to focus in on all the numbers, which is really important, but we also want to see what other things are happening. Like I said, maybe you mix something together in a solid form. That's a really important observation to record, not qualitative of just made a yellow solid, made a white solid, whatever it may be, formed. Or there was bubbles that occurred, which is a really important aspect of just a qualitative analysis. That would usually indicate that you actually made a gas, because that's what's probably making the bubbles and stuff like that. So when we're in the laboratory, we do want to always sort of record both of those things. But when we do something that's quantitatively or a quantitative sort of measurement, it should be pretty exact and as exact as it can be. Now, one of the things that we deal a lot with in chemistry is really large numbers and really small numbers. And as you can see there, that's a really large number of 602, and a bunch of zeros. I won't count them. There's probably like 20 of them. And also the mass of a hydrogen atom is 0.00, a whole bunch of zeros there, and 166 at the end. Now, obviously, if you're using these numbers in some type of calculation, there's probably a fairly good shot. Yeah, you're going to lose a zero along the way there, or miss a zero or something like that, especially if you have a lot of those. So we do use scientific notation a lot to handle really big numbers and really small numbers. Scientific notation basically has this general formula of n times 10 to the n. This first n is a number between 1 and 10. Now, it can actually be 1 when you write something in scientific notation. It cannot be 10. So it's got to be less than 10, and it can be 1 and above, basically, but usually we don't use 10. And times 10 to the little n up there, this will either be a positive or negative number. And that really depends on how many places you need to move the decimal point to get to a number between 1 and 10, and which way you move the decimal point as to whether or not it's going to be positive or negative. So if I have something like 3, 2, 5, 6, and I want to write this in scientific notation. Now, in this particular case, there is no decimal point written, but we usually would assume that the decimal point in this case would be at the end, right? So we would assume it would be at the end. So in this case, we would move the decimal place one place to the left. That would give us only 325.6, which is not a number between 1 and 10, right? If we go one more place to the left, we're at 32.5, which again is more than 1 through 10. We need to go one more place to the left, and now we have something that is 3.256 times 10 to the 3. The 3 is how many places I moved the decimal point to get to a number between 1 and 10. It is a positive number there. As you move the decimal place to the left, you should end up with a positive exponent up there on top. The way to remember it is big number, large number will have a positive exponent. Yeah, so anything above 1 will have a positive exponent. Now, if I had something like 0.032, in this particular case, I actually do need to move the decimal point there to the right. And if I go one place to the right, I'm only at 0.3, which is not a number between 1 and 10. I do need to go one more place, and I will end up with 3.2 times 10 to the minus 2. Obviously, the 2 here in this case is how many places I moved the decimal point. And you can see in this case, I went to the right, which means it will be a negative exponent up on top. And that's really important as well. So if I had something like 0.05003320, in this particular case, we would go one place, two places, and that would get us to 5.00320 times 10 to the minus 2. Now, you may be wondering in this particular case, why am I keeping all those numbers, right? And there is a reason why I'm keeping all those numbers, and we will talk about it very shortly as well. But basically, all those numbers are significant figures, and we do not want to lose any significant figures when we go from like decimal form to scientific notation, or scientific notation back to decimal form. So we want to be careful with that, and we'll talk about why all those are significant in a bit. But we do want to kind of keep all the proper number of significant figures as we kind of go from one place to the next. By the way, one of the advantages of scientific notation in terms of writing is all the numbers, when you write something in scientific notation, all the numbers before the times 10 part, these are always significant figures. So if you see a number that is properly written in scientific notation, when you look at the number before the times 10 part, that will tell you how many significant figures it has. So for example, this one right here would have 4 significant figures. as all those numbers are significant. This guy over here would actually have 6 significant figures, as all those are significant. And obviously here, this guy would have 2 significant figures in this case. Now, one of the advantages of that is when we start talking about truly doing calculations and given our answers in the proper number of significant figures, there sometimes is only one way that you could achieve that. And the only way that you could achieve it is actually to write the number in scientific notation. There are sometimes answers that you get that you cannot leave in like decimal form and have the right number of significant figures. No matter how you want to do it, there's no way to do it. This is a way that you could do it. Why is this a good way to do it? Because frankly, if I had a number like 1.2 times 10 to the 3, how many significant figures would that have? It would have 2 significant figures. Yeah, the way it's written. Now, let's say I needed 3 significant figures. All I simply need to do is something like that. Now it has 3 significant figures. Let's say I needed 1 significant figure. I could just do something like this. Now it has 1 significant figure. So kind of when you write a number in scientific notation, you could actually control how many significant figures that you're writing. And that gives you the option of, like I said, in some cases, that's the only way you could kind of get the right answer and the right number of significant figures is to write it in scientific notation. By the way, we'll talk about it as well, but when the number is written in scientific notation, we look at it as it's written in scientific notation to decide the significant figures. We don't try to turn it into like a decimal guy number to figure out how many significant figures it has. Any questions on that? Now, do you always have to write answers in scientific notation? The answer is, for me, no, but there are some teachers that always want you to do it. But for me, you do not have to do it unless obviously the instructions say to do it, that you need to give it in scientific notation. Or like I just mentioned a second ago, there's really only one option. You have to kind of do scientific notation to get the right number of significant figures for your answer. Now, writing scientific notation is really important, but let's talk about really the most important thing about scientific notation, which is, you know, how to use your calculator correctly with scientific notation. That's probably more important than maybe just being able to write it, is to how to actually punch it into your calculator correctly. So we'll talk about how to do it on multiple calculators, since you may have a slightly different calculator, and then we'll point out the way, on that calculator again that you're going to have to use for tests and quizzes, how to do it. But if you look at your calculator, there's a couple really important buttons when you're trying to punch a number in scientific notation into your calculator. And on most people's calculators, there's usually one of 3 buttons. There's either an EE button, there's either a EXP button, or the third option, and this is usually the option if your calculator is kind of like a two-tone calculator. It has like a main color in the front and the back is like a different color. That's usually this last option. And that is an actual button that says, actually, no, it says, I think here, it will say actually times 10 to the n. And if you have that, you usually also have like a little wheel on your calculator, kind of to the right, upper right. You'll have that like little wheel kind of thing going on there. Now, we're talking about each of these things in just a second. The other important button is actually your negative button, I call it, or your change of sign button. And on most people's calculators, it is usually a plus or minus, or it may just be like a parentheses with a minus in it. It is not the subtract button. So that's really important as well. You do not want to use the subtract button here. So let's talk about how we would punch a number into the calculator correctly using scientific notation. So let's just say we had 1.25 times 10 to the minus 6. And we wanted to write that or type that correctly into our calculator. I'm going to talk about these 2 buttons first, and then I'll come and talk about that sort of combination over here. What you would want to do is you would want to type in 1.25, and then you would want to hit your exponent button, either one of those 2 on the left there. You would want to hit it. On your screen, you will see probably one of 2 things. you may see a 1.25 and an E, or you may see like 1.25 and a couple of zeros kind of pop up to the top. And a combination of that is you might also see 1.25, a very small times 10, and a couple of zeros pop up as well. So this is typically what you will see. Now, when we hit that exponent button, the very important part of it is it represents in the number, when you hit this button, it represents all of that right there. Yeah, it represents the times 10 part of the number. That means that you should never use the multiplication button when you're doing this. And by the way, you should not use the shift log button because that is the incorrect way of using it in scientific notation. You will get the wrong answer most likely. That is the number you want to put in there. That means really the only thing left we have to put in there is the -6 part. And that's where your negative button would come into play. You want to hit your negative and then 6. And this will become -6. This will become 6 in the negative. This will become 6 in the negative. And that is the proper way to punch in this number in scientific notation. Now, if you have this combination here, you have to do a similar thing, but because your calculator is programmed pretty crappily, you got to tell the calculator what you're doing. Because if you don't do it exactly like this, the calculator will think your numbers are different and it will do the wrong math for you and you'll get the wrong answer. So if you happen to have this combination, which again, as I mentioned, is usually on like a two-tone sort of calculator, you actually need to start with a parentheses. So you need to open up a parentheses. And then you need to do 1.25. You then will hit your exponent button. And what you will see on your screen is parentheses 1.25 times 10. And what you will have right there is your little cursor thing blinking up towards the top. Yeah. At this point, you could kind of roll just like normal. You're going to find your negative button. You're going to hit your negative button and your 6. And you will end up with something that looks like this. And you will still have your little blinker cursor number up on top. Now, the problem with your little cursor being up on top is if you close the parentheses at this point, you probably get an error in a lot of those calculators because it's like parentheses the way up on top. It's not good. So you actually have to bring the cursor back down. And that's where the wheel comes into play. You will take your wheel, and typically you will hit the right-hand side of your wheel. That will move this down to a regular spot and not a superscript. And now you could close your parentheses and you will end up with 1.25 times 10 to the minus 6 and a big parentheses on the back end. It looks like a lot of steps, but obviously you can do that pretty quickly once you get the hang of it. But the key with that type of calculator is you do need to kind of put parentheses around every single number that's in scientific notation. Otherwise, it will break up the numbers incorrectly and give you the wrong answer on those type of calculators. The other calculators that have the EE button and the EXP button, you don't really have to be super careful. You don't need parentheses. You can kind of roll with it, and usually you'll be in good shape. Now, the one that you will be using for quizzes and exams, I believe has the EXP button, if I'm not mistaken. I do is that calculator. There it is. So on this calculator, which obviously is the one that you'll use for quizzes and exams, this one has the EE button. Yeah, so right around here is the EE button that you would use. So on this type of calculator, which you'll use on exams and quizzes, if you buy it yourself, you could practice with it. You would roll this way with it, yeah, on this particular calculator. Yeah. And the negative button is down here is the plus and the minus button as well. So the one that you'll have to use will have those buttons on it. Any questions on, more importantly, how to punch them in correctly? Common errors that people make, like I said, when they try to do this is they want to use that multiplication button and they want to do like the shift log. You should never use the log button when you try to do scientific notation. You should not use the multiplication button unless you're multiplying the number. And you should not use the subtract button for a negative, otherwise you'll run into error. By the way, your calculator will not always give you the answer in scientific notation. and it will not always give you to improper significant figures or anything like that. So just keep that in mind unless you program the calculator to give it to you in scientific notation. So let's try a couple here just to kind of see, make sure everybody can figure out how to do it here. Let's erase that. So why don't we try, let's take uh, 2 times 10 to the minus 5. Let's divide it by 4.22 times 10 to the 6. And let's go 1.2 times 10 to the minus 3, and we'll times it by 4.1 times 10 to the minus 8. All right, so punch those in and see what you come up with. I'll do it as well. Hopefully come up with the right numbers here. Okay, let's take a look and see. So again, I'm going to show you how to punch it in. Again, probably using the first method, which is kind of like the one that you'll be using. Again, if you have the other calculator, you got to do some parentheses around everything. But here, what I would want to do is go 3.2. I would want to hit my exponent button, and then I would want to hit my negative button and 5. And again, that would represent obviously that first number. I then want to hit my divide button. I want to punch my next number in the same way, 4.22. Once again, I'm going to go exponent button, and I'm going to go 6 in this case, as it's not a negative exponent, so I don't want to use a negative here, right? Otherwise, it will definitely give me the wrong answer. And I probably want to hit equals, yeah. And if you do all that, you will end up with, let me see here, 3.2. You will end up on your calculator something that looks like this. 7.58 2938 Now, on the one that you'll use in class, it will also look like this, minus 12. On other calculators, you may see 7.5829383889E minus 12. Yeah, so those are two of the ways that most likely it will kind of just spit it out to you. So a couple of things here. We do not want to keep all those numbers, and the proper answer here at the end would be something like 7.6 times 10 to the minus 12 would be our proper answer. And we'll talk about why the sig figs end up that way a little bit later, but we would round that. Most importantly, the reason why I'm showing you kind of on the right there is a very, very common error that people do is when they look at their calculator and they get their answer, they tend to only look at like this part of it. And a lot of times people will just write 7.6 as the answer and forget about sort of the back part of the number. So you don't want to forget about the exponent part, which is typically displayed like this. On this calculator that you're going to use, it doesn't say times 10 or anything like that. It just kind of puts the exponent part up on top. So you want to make sure you don't forget that part of the number when you're going to do it. Or over here, that is what the E represents, the times 10 again, and the minus 12. So you want to make sure that you do get the exponent part of the answer. And like I said, that's a very common error people make. They just kind of just look at the big number in front and they forget about like, oh, it's actually times 10 to the sum power. So you want to make sure you not do that. The way I wrote it there on the left is the way that you should write scientific notation. And what I mean by that is you should write 7.6 times 10 to the minus 12. You should not write as an answer if you're given it. You should not write this, E minus 12. That is not the way to write proper scientific notation when you're writing it as an answer or anything like that. Although calculators, computers use the E as the times 10 part. When you are writing the answer, you do need to write times 10. Don't use that E for the times 10 part in your answer or when you're writing it. Any questions on that there? Taking a look at the bottom one, we're going to kind of punch it in the same way. By the way, if you have the other calculator, the only difference is you got to throw parentheses around it, right, before you kind of do that. If you're going, we're going to go 1.2. We're going to hit our exponent button. We're going to hit our negative button here and our 3. We're going to hit our multiplication button, and we go 4.1. Once again, exponent button, and that was -8, I think. So we're going to go negative and 8 and hit equals along the way. And if you do that, you will end up with 1.2 exponent -3 times 4.1 exponent -8. And you will end up with, on your calculator here, 4.92 -11, or you may have 4.92e -11. So there's, again, 2 common ways. So our answer in this case would be 4.9 times 10 to the minus 11. So again, we want to make sure we don't miss the exponent part of it. Any questions on that? Now, a couple of things about calculators and scientific notation. Like I said before, you may actually put a number in scientific notation, and if it's able to do so, for example, on a calculator like this, it may just automatically convert it into a decimal, which is okay. Yeah, so it'll just automatically kind of convert it for you. And then some will just keep it in scientific notation. Any questions on how to properly punch those things into the calculator there? All right. So obviously that's what we talked about, the n times 10 to the n. All right, then again here, a couple of examples of writing a number in scientific notation. So once again, looking at our first number here, none of these are negative. That's just from PowerPoint. We're going to go 1 place, 2 places there to the left. And again, big number, going to have a positive exponent for 2. Here we're going to go 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places. Again, smaller number, going to have a negative exponent as we move it there to the right. And you get 7.72 times 10 to the minus 6. Here we assume the decimal points at the end. So 1, 2, 3, and 4 gives us our 1.25 times 10 to the 4. I'll write the last one here. This is getting cut off. We're going to go 1 place here to the right, 1.35 times 10 to the minus 1. Any questions on those there? So the next thing we're going to actually talk about here, which is a really important thing, and we'll get a lot of practice next week when we do the experiment, and that is how to take a proper measurement. So there's always some type of uncertainty in a measurement that you take. So regardless of any measurement that you make, there's a estimation that occurs. There's some uncertainty with that measurement that you take. The amount of uncertainty depends on the piece of equipment that you're using to take that measurement. Some things are really good, and some things are not the best things to do with measurements, and there's error associated with any type of measurement. So let's just take a ruler, for example. And we'll go 1 and 2. My bad ruler there. We'll call these centimeters. All right, so let's say we have this ruler here, and I want to measure like an arrow-ish, something like that. All right, so the first thing, whenever you look at any piece of equipment that you're going to take a measurement with, there's really 2 types of numbers or markings that you want to look at. There are what are sometimes referred to as large markings. Large markings are the one where you look at the piece of equipment and there's actually numbers. So there's actually numbers on those things, or the typical large markings. Now, in this particular case, I have a large marking at 1 and a large marking, next one is at 2. That means the difference between that is how many centimeters? Yeah, the difference between 2 and 1 is 1 centimeter, right? So the large markings on this ruler represent 1 centimeter, right? There's a 1 centimeter difference between them. Now there are small markings on, and not in all cases, but in most of the cases, the small markings typically don't have numbers associated with them. They are the markings that fall between the ones that do have numbers. Sometimes the large markings and the small markings are the same, but in most cases, there's small markings between those larger markings. And in this case, those are all the small ones here that do not have numbers associated with it. We want to count how many we have of those, and we do want to count these small markings correctly. So when we're counting small markings, we always start after the last large marking. So on my particular ruler here, we would start counting here as 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we continue to count until we hit the next large marking. So when we're counting the smaller guys, we start after the large marking and end at the next large marking. So there are 10 little markings between my large marking of 1 centimeter. That means each little marking represents, small marking represents how much? Each one represents, if we divide this by 10, 0.1 centimeters, right? So 0.1 of a centimeter is basically what it represents. This would be then 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2 as we get over there. Now, when we take an actual reading of this, there should always be numbers that no matter who looks at it, pretty much everybody should agree. So if you looked at this terribly drawn ruler here, we should all hopefully agree that it is at least 1.5 down the road there. Yeah. It's not exactly 1.6 and it's past 1.5. So we would record 1.5 in this case. And these are what are represented in our measurement as all the certain numbers. So these are all the certain numbers that are represented here. And again, these are the numbers that really nobody should argue about. Everybody should agree it's at least that much. The problem is, obviously, in this particular case, I am not exactly at 1.5. And again, I'm not exactly at 1.6 either. I need to, in this case, make an estimate of where I think that arrow sort of stops. In this particular case, I may look at it and go, maybe it's not exactly halfway between them. Maybe it's a little bit further, and I may record something like a 6. And obviously my centimeters as well for my units. This is what is sometimes referred to as the first uncertain number. And when you take a measurement, you always want to record all the certain numbers plus that first uncertain number in this case. And that would be the proper measurement in this case. The reason you want to always record all the certain numbers plus the first uncertain number is when you take those things together, that is what significant figures is. So that would mean in this particular measurement, my number would have how many significant figures? It would have 3 significant figures, with the uncertain number or the estimated number being that last number. What you're really saying when you write 1.56 in this case is, I think it's 1.56, but it might be like 1.57. It might be like 1.55. It's somewhere in that ballpark. I'm unsure in that last little spot where it's at. And that's where the uncertainty lies in this particular measurement. You could also, when you look at a scale, you do want to be careful and you want to look at the scale. So let's just say we took you'll find out why I was not an art teacher very shortly here. I'll go 20. We'll do milliliters. And let's just say we took a liquid here. And by the way, when we put a liquid in a glass container, we typically will see the curvature of the liquid, which is known as the meniscus, exaggeratedly drawn like that, like a U. And we typically want to read from the bottom of the meniscus. And that is because what's actually happened here, and we'll talk about in a later chapter, is the attraction between the liquid and the glass is stronger than the attraction between the liquid and itself. So where the liquid touches the glass, it starts to rise up the sides of it through capillary action. And it creates this typical U. There are certain things like mercury that will go the other way, but most things will do like a U sort of meniscus in this case. So we want to do the same thing here. We want to look at our large markings. And in this case, that is 10 milliliters. That is 20 milliliters. That is a difference of how many milliliters in this case? 20 minus 10 is 10. Yeah, so that's a difference of 10 milliliters. We then want to count our small markings in this case. And again, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we got 10 small markings. So in this particular case, each of the small markings represents how much? So 10 divided by 10 is 1 milliliter. Yeah, in this case, each of these markings represent 1 milliliter. That's 11, that's 12, 13, 14, 15, 16, 17, 18, 19. So when I look at my meniscus here, I am at least at 15, which I would want to record. Again, that's going to be my certain numbers. Again, I'm not exactly at 15, right? I'm not exactly at 16. In this case, you may feel it's maybe between those two. So maybe we would record 0.5 in our unit, milliliters. This would be my first uncertain number. That would mean in this particular measurement, this number has how many significant figures? It has 3 significant figures. All 3 of those are significant. The uncertain number is that last number there. And what you're really saying in this case is I think it's 15.5, but maybe it's like 15.6, maybe it's like 15.4, it's somewhere in that ballpark. I'm going to guesstimate it's like 15.5 in terms of its milliliters. Question on that there. All right, we're going to wrap it up here.